While this probability doesn't make a big difference, you'll notice that 16 over 100 here, as opposed to 16 over 90 here, this is going to be a larger percentage or larger probability than this one is going to be up here. So, because you've reduced the size of the pool, you would expect the probability to be a little bit higher in favor of catching one of those black fish. Now you only have one blue, although it's not very big to begin with if you think about it. Well, what's the probability that we get a blue the first try and a blue the second try? Again, we simply can't do 2/10 times 2/10 because that assumes that each time the probability is the same. Now, when the pool is large enough, we say that when the pool is basically infinitely large, as in if there were millions and millions and millions of fish and 20% of them were blue and 80% were black, then we probably wouldn't need to update the probability once we draw one. Because if there are millions of fish, what does one fish do to the entire pool? Probably won't make a big difference. But if you only have 10 fish, removing one can significantly affect your probabilities. So, what we're going to say here is, well, it's got to be 2/10 for the first fish. But now that you've removed a blue, you only have 9 fish left. And out of those 9 fish, there's only one more blue. So now the probability has gotten a little bit smaller. And basically we've gone to 2/90ths. Well, what are we actually multiplying here? This equal sign is actually multiplying the probability of getting a blue fish on the first time times not the probability of getting a blue fish on the second try, but the probability of getting a blue fish on the second try given that the first try resulted in a blue fish as well. So here's our condition, and this probability right here of getting a blue fish the second time around is dependent upon knowing that we've removed one of those blue fish from the pool. So what we can say in general is that for events A and B, the probability of A and B is equal to the probability of A times the probability of B, provided the information given to us by event A having happened. Now, if A and B are independent events, guess what's going to happen? Doesn't matter whether they're dependent or not here. This just says take the probability of the first thing, multiply it by the probability of the second thing, keeping the condition that the first thing happened in mind. So if they're independent, this will just end up becoming the probability of A times the probability of B, if independent. So really, our rule doesn't change here at all. It's just we need to keep in mind that we need to modify the second probability, assuming the first one's happened. Okay, that also leads us to an important result, which says if we manipulate this formula, divide both sides by the probability of A, we can get the conditional B given A by taking the probability of A and B and dividing it by the probability of A. So this is a very useful result as well. This is useful when you're trying to calculate A and B. This is useful when you're trying to calculate B, given that A has occurred. So we've actually used this tool already. Let's look at an example. So let T be the event that a person buys a new TV. Let H be the event that the person is happy. And let's say that these are all the outcomes. So 55% of the time people are happy regardless, 45% of the time people are not happy, and 40% of the time a person has bought a new TV, and 60% of the time they haven't. And then 30% are happy and they own a TV. We don't know why they're happy. We don't know why they bought a TV, but the 30% of them are in that case. So given that a person buys a TV, what is the probability that he is happy? Okay, well, if you bought a TV, then you're actually here in this category. You're actually in this column. And if you think about this as being scaled out of 100, since it's 100%, or since these are percentages, then that means 40 out of 100 people have bought a TV. Okay, well, that's the probability of buying a TV. And out of those, 30% are happy. which if you divide